Hello. Today we are going to see how we can rearrange the PID controllers implemented in the third practice so we can obtain the desired results, deleting the effects of having undesired zeros on the closed loop system. On practice 3, we designed a PI controller for the velocity control, and afterwards, we designed a PID control for the position shaft. In this practice, we will follow the same steps. First, we will rearrange the PI controller, and we will then rearrange the PID controller. In order to control the velocity of the motor, let's first remember its transfer function and set some control objectives. As we can see, the motor in open loop, taking as output the dynamo tachymetrix voltage, resembles a first-order system which has been discretized by a first-order holder. As we decided on the practice before, we want the closed-loop system not to have overshoot and to get the reference with a settling time of 0,8 seconds. As we saw on practice 3, the obtained closed-loop transfer function of the PI velocity control had 2 poles and a 0. By means of the controller's parameters we were able to place the poles and design the stability and the temporal response of the system. But placing the poles by the controller's parameters in this architecture has a drawback. As we can see, the 0 is also automatically placed when placing the poles, so we obtained an undesired overshoot, as we can be seen in the following figure. We designed the PI controller such that we stabilize the plant in 0,8 seconds with no overshoot, but the obtained system didn't fulfill the specifications. So we will introduce another architecture when designing a PI controller in a first-order plant. As in this case, things get complicated because of the closed-loop 0. This figure shows another alternative manner to introduce the proportional and integral actions. This control structure takes the name of IP controller. As we can analyze, the denominator of the obtained transfer function is the same as in the case of the PI controller. What it has changed is the numerator of this new scheme. As we can see, now we obtain a 0 and z equal -1. It is worth to comment that the proportional action of the IP controller doesn't see the reference, so the response of the closed-loop system to a step input of a IP controller is smoother than the one with the PI. As the denominator of the closed loop is the same as the one obtained in the practice 3, the equations used to tune the controller parameters are exactly the same than those used for the PI controller. On the following image we can analyze the simulation of both responses. The blue response corresponds to the PI controller, while the green one corresponds to the IP controller. As it can be seen, IP controller allows to obtain the desired dynamics without the additional overshoot. So, this Simulink block diagram has been designed for the IP implementation. In this video we can see the system's behavior with the proposed IP controller. A step response with a settling time of 0.8 seconds and no overshoot has been imposed. In this figure we can analyze the responses of a simulation done before implementing the controller in the real system, in blue, and the real response, in green. As can be observed, the two responses are practically the same, and so we can say that specifications are met. In order to control the position of the motor, let's first again remember its transfer function and set some control objectives too. On one hand, as we can see, the motor in open loop, taking as output the potentiometer's voltage, resembles a second-order system which has been discretized by a zero-order holder. On the other hand, the desired closed-loop dynamics must follow an oscillation frequency of 0,5 Hz and an 80% of overshoot. In the case of the position control, we obtained a closed-loop system with 4 poles and 3 zeros. Two main problems were identified when closing the closed-loop system. On one hand, we have 4 poles to fix by 3 parameters. This means, one of the poles was freely fixed and we had to check whether this pole was stable and not dominant. On the other hand, we obtain 3 zeros, which affect the dynamics of the closed-loop system. So, let's see how to improve this controller in order to delete those effects. From the 3 zeros, 1 zero comes from the plant and the other 2 from the controller. And as we can see, as in the case of the velocity control, when placing the closed-loop poles, the zeros are automatically fixed, as they depend on the controller's gains too. So, we will modify the structure of the controller to delete the effect of the zeros. In this new structure, the 3 actions of the controller are embedded. As we have done before, the input of the integral action is the error, while the input of the proportional and derivative actions is the output of the system. This control structure takes the name of IPD controller, but we still have 3 parameters to fix 4 poles, so, a new parameter is added. By adding this new parameter, we will be able to fix the 4 poles by the 4 parameters. So, let's analyze the closed-loop transfer function. If we check now the numerator of the closed-loop system, we can see that now the zeros are not dependent on the controller's gains. Finally, the coefficients of the denominator of the closed-loop system have been matched with the coefficients of the desired characteristic equation, where the specifications told in practice 3 are embedded. The desired closed-loop dynamics must follow an oscillation frequency of 0,5 Hz and an 80% of overshoot. On the following image we can analyze the simulation of both responses. The blue response corresponds to the PID controller implemented in practice 3, while the green one corresponds to the IPD controller. As it can seen, with the new structure, the desired dynamics are obtained. For the IPD implementation, this Simulink block diagram has been designed. In this video we can analyze the system's behavior with the shown IPD controller, where the reference varies from -2 to 2 volts. The control has been designed such that the system has an 80% of overshoot and a natural oscillation of 0,5 Hz. In this figure we can analyze the responses of a simulation done before implementing the controller in the real system, in green, and the real response, in blue. As we can see, the real response doesn't follow the simulated response. This is because there are non-modeled dynamics and so the obtained transfer function doesn't exactly represent the whole real system.